This is StarTalk. Neil deGrasse Tyson here, your personal astrophysicist, and today is a Cosmic Queries edition. And we titled this one, Sounds of the Universe. Ooh, Sounds of the Universe. And there's only one person who is editor-in-chief of the Sounds of the Universe, and that's Kim Arcand. We'll get to her in just a moment. Let me introduce my co-host, Matt Kirshen. Matt, welcome back to StarTalk.
Oh, it's a pleasure. Thanks for having me, as always.
Yeah. Host of Probably Science. And
that's right.
Just all around funny guy. We love you when you come on. So thanks for.
I love being on. Also, I've recently just had a couple of messages. I'm on a tour at the moment, and just had a few tweets from people who were like, "I didn't know you were on this show. I know you from StarTalk."
Oh my gosh! Excellent. That's how it's supposed to work, you know.
Exactly. So, hey, StarTalk listeners who've just seen me on stage, it's nice to also see you through the screen.
We have Kim Arcand as our expert guest. She's been a StarTalk visitor before, many years ago, pre-COVID, before COVID, BC. I think we should call it that, right?
Yep.
She's a visualization scientist and was an engineering tech lead for the Chandra X-ray Observatory, a very important space observatory, on the ranks of Hubble, except its data was in X-rays, so it didn't quite get all the PR that Hubble got, but it was one of our great observatories that we put into orbit around the Earth to see the universe in X-rays. And she works on several projects. We're interested in the stuff she's done that connects the acoustic world to the cosmic universe. And some of the stuff she's done has even went viral. And so Kim, welcome back to StarTalk.
Thanks. It's so great to be back.
So what is NASA's Sonification project?
Well, the Sonification project essentially is just a way that turns NASA data into sound. That's all it is. It's like data storytelling, but using our ears to hear it instead of just our eyes to see it. It actually started as a project because during the pandemic, I really wanted to be able to keep working with my community members and colleagues who are blind or low vision. And our previous 3D printing program just became very challenging during the pandemic. You couldn't be in the same room with someone, never mind share a 3D print. And so we started converting data into sound, and it turned into a much bigger thing than I expected.
So this is not just for grins. This is because it really can serve the needs and the desires of the seeing impaired. I mean, that's...
Yes.
I mean, it's not just, oh, that's cool. No, it's like, oh
right.
My gosh, how else are you gonna feel this?
Yeah, absolutely. We had, like I said, been working in 3D printing primarily, so translating data sets into 3 dimensions that we could 3D print whole, or into tactile plates where you could kind of create like relief maps from the data. But then during the pandemic, that was just all kind of impossible. So I recalled a colleague that I had met at a visualization conference, Matt Russo. He's part of System Sounds, and he and his partner, Andrew Santaguida, had been working in some cool areas of data sonification that I thought would be great to bring towards the Chandra Data. And so we started working together, and we created a few sonifications, and they were very well received. And I think I was very surprised at that. I thought it would be, something we created for and with people who are blind or low vision. So I don't know why. I just didn't expect it to go beyond that community, but it really did, and it was very lovely to witness that.
So Matt, I got an idea for her. You want to hear me? You want to hear my new idea?
I'm listening. I'm all ears.
They started out with 3D printing, all right? So that's
yes.
Your sense of touch, if you otherwise don't have a sense of sight, all right? And then COVID put a kibosh on that, and they switched senses. Because we got 5 traditional ones, right? So why get stuck on one? So then you went to auditory data, and I'm thinking, why not go to taste?
So I'd stop there. Like, just
no, we can taste the data.
Yeah,
I don't know. I feel like the taste and the smells might be scary, like sulfur, iron. I don't know if I want any of that.
Yes.
Rotten eggs? No, thank you.
Hydrogen sulfide in the universe. And,
yeah.
Oh my gosh, this is the next thing. Okay.
No, I think we're good.
So just so I can get a grasp on this, because I think obviously this is Neil's world, but this is you've got a map, or you've got these you've got these images that are coming through that are X-rays or radio waves or whatever, and you're converting them into sound waves directly.
So yeah, what is happening? Right. So all this data that we're capturing, say with Chandra, that's all X-ray light. So nothing that humans can naturally see, right? So humans do this amazing stuff where they build these crazy spacecraft that can capture that data and then write this awesome software that can translate that data. Because essentially astronomy like that is just numerical, right? So we're translating that into something we can see, that visual representation of the object. And then from there, the pipeline is to sound. So we essentially take all of those pixels that we get from that resulting image and we do a mathematical mapping from those pixels into something we can hear by using like assigning different kinds of sounds, either a synthetic sound or like an instrumental sound, for example.
So the whole picture, though, is seen all at once, whereas sound has a beginning, middle, and an end. So
yes.
Are you scanning left to right across the image, and then it comes into, quote, auditory view, if I can borrow that word,
yeah,
and then
that's
goes
a
back
great
out
question.
again? Is that how you do that?
Yeah, and that's a great question because it actually brings up some interesting things of why this has been such a fun project. So it depends on the data set is the short answer to your question. If it's a sort of landscape shaped image, if you will, then we'll scan from left to right. If it's like tall and skinny, then we usually scan either top to bottom or bottom to top, depending if we're trying to use stereo sound or whatever the data is showing. If it's an object like a supernova remnant that's got very sort of spherical structure, then we typically do center out or a radial scan, right? So we let the data drive the process. It's a bespoke process still at this point, but it's really taking the science that's all tucked up inside those images and letting that drive the data sonification.
That makes complete sense now that you say
good.
it. Of course.
I'm glad. Thanks.
Yeah, if you have a spherically symmetric object, you want to sample that in a spherically symmetric path, right?
Exactly.
That makes complete sense. You want to match your geometry to the geometry of what it is you're presenting. But now, I got a bone to pick with you.
Yeah.
Okay?
Matt,
I need backup on this in case she gives me a hard time here. You ready? Okay.
Yep.
You are leaving people with the impression that these objects in space are
yes, I see where you're going with this. So yes and no.
Okay, but I know.
Yes and no.
No, I know because I saw the movie that in space no one can hear you scream. I saw Alien. That's how I knew. I didn't know before then, of course.
That was such a good movie. It was such a good movie. I love that movie.
This is why rockets don't have car horns.
Right. Get out of the way.
Exactly. Exactly.
It's
a great point.
So is there some what's the term? Is there some housekeeping you have to do at the end of all of this to say we're not actually hearing the universe?
Yes, so I have two answers to that. And the simpler one is yes, we always say we're not holding a microphone up to the sky, right? We're not recording actual sounds. We're too far away from any of these objects, even if they were making sounds. However, there are objects in the universe that do create sound waves. And so one of the sonifications I think we're going to listen to on this show today is actually
you brought clips. Yes,
waves.
I want to make sure.
We have some clips.
Yes, I will totally. Before we get,
cool.
By the way, this is a cosmic query, so we just laying some landscape here.
Laying the good thread in our garden.
In the garden, yes.
Yeah. So yeah, there is this idea that there is no sound in space, but that's not really true. You know, there are sound waves that are occurring in things like galaxy clusters, where there is all this super hot gas around things like supermassive black holes. And a supermassive black hole might have, like, say, a relativistic jet coming out of it. And if it's surrounded by all of that super hot gas, the jet is kind of like the drumstick and the hot gas is like the drum, right? And it can create sound waves. So we do have an example where we've taken a sound wave and resonified it up to something we can hear.
Okay, Dan, why did you just convince me? I didn't want to be convinced. I wanted to argue with you about this.
I love to argue. No, arguing is so fun.
She's right. Oh my gosh.
Yeah.
Okay, what you're saying is wherever there's gas in the universe, which is in many places, it's reasonable to say what is sound doing in that gas because the sound is moving through a medium. Right. It's the vacuum of intergalactic space or wherever there is no gas that brings in the
exactly.
That's where you have the issue.
And we're not going to hear anything here on Earth. We're too far, and these sounds are way too deep and all of that. But out there in outer space, there are places where there are sound waves occurring. And even like the early universe, you know, the sort of that early archaeological history, if you will, like the cosmic microwave background, like when there was all of that, dense, hot fog.
Right.
They can translate that information into sound and kind of learn about things
Authentic
differently.
sound, not just a
not
conversion.
just right.
Right.
So
An
I know,
image conversion. Yeah.
I know audio gearheads are always like trying to search for like the deeper basses and like the bigger and bigger subwoofers. Like how deep are these galaxy clusters getting? Like what?
Wait, Matt.
If one of them was mounted on the
Matt,
back of someone's Volkswagen Golf, like how?
So I can tell
wait,
you.
Matt. I'll ask that question. Ready?
Okay.
Kim, how deep can you go?
You do have the perfect voice for that question.
How deep can you go?
Very
Yes,
deep.
okay.
So for example, the Perseus Galaxy Cluster, which is like a couple 100 million light years away from us, so pretty far, that black hole is singing out at a note that's, oh, I'm sorry, my cat's saying hello, singing out at a note that's about 57 octaves below middle C. And so that is, I think, one of the deepest. It's possible that M87 is also deeper, but it doesn't sing as well. So hold on, let me just move my cat so my microphone's not getting messed up. But so that is, as far as we are aware, at least one of the deepest notes in the universe. 57 octaves below middle C at B flat.
Okay, so all of these notes, even those that are not the deepest, still fall well outside of our 20 to 20,000 hertz, auditory range. So in order to hear these sounds, you have to, I don't want to say fake it, but you have to boost it. Change, yes. You have to put it in another octave where we can hear it. You got to do that. Okay.
Yeah, exactly. So in the sonification project for that, we re-sonified it by bringing back up about 57 and 58 octaves so that we can hear it.
I like that, re-sonify. You got your own vocabulary for this.
Yeah,
Damn.
we kind of have developed it. And
Damn.
I have to give such credit to my partners, Matt and Andrew, on this project because we really thought hard about this stuff. And they've definitely tried to lay a lot of groundwork. It's a very exciting thing.
So what's the first clip you have?
The first clip is a general sort of introduction to what sonification is. And this is just translating an image into sound. So there's no sound waves that we're capturing here, although this is a supermassive black hole, so there could be some. But this is the inner 400 light years around Sagittarius A star, our supermassive black hole at the center of the Milky Way. And what's cool about this data set is we've got 3 different kinds of light. We've got light from the Hubble Space Telescope, that's kind of like optical near infrared. We've got Spitzer Space Telescope infrared data, and then we've got the Chandra Data in X-ray, right? And so all 3 of those layers combined, it makes a beautiful image. It's red, yellow, and blue, respectively, from low to high energies. And it's very rich, but very dense. So, the area around our supermassive black hole, it's like Times Square, right? There's a lot going on. It is the downtown of our Milky Way region. There's just a lot happening. There's all kinds of exploding stars, large stars, lots of gas and dust, really cool stuff. But
stars getting eaten, probably.
Stars getting eaten, asteroids getting snacked on, all sorts of great stuff, right?
Yeah.
So the image itself is very busy and dense. And when we listen to it, what we've done is we've assigned each of the types of light a different sound. And so the lowest energy is a very soft piano. The medium energy from Hubble, that's like a plucky violin. And then the highest energy from Chandra, that's like this, pringly little glockenspiel sound. And so we're scanning across the image from left to right as you're
Wait a minute, you get to pick your own instruments?
We do.
Yep.
Yes.
Exactly. Who put you orchestra instrument in chief person? Who
we did. We self-selected, I guess. Yeah. And I should say, to be fair, I'm a former band and chorus geek, so I have some music sort of theory under my back. Also, Matt is actually a musician today, like he plays in a band. And he's also an astrophysicist. And then Andrew is like an amazing musician and sound engineer too.
Okay, so you have the right, you got the chops. You got
a
the
nice mixture. I won't, exactly. So we're self-selected.
But it seems to me you could choose instruments differently so that the center of the galaxy feels kind of bluesy. Or
absolutely,
or hard rock, or country, right?
How do you want your universe to sound like? Exactly, right? Kazoo. That might.
Matt, what did you say? A kazoo? Yeah.
Yeah, and a slide whistle. I want
slide whistle, a kazoo, and an accordion.
Yeah. But sure. What do you want your universe to sound like? That is a question because we are absolutely picking instruments based on the science story that's in that data that we're trying to communicate, right? So we want the three layers to be distinct from each other, because
Mm-hmm.
that's one of the key things, particularly for people who are blind or low vision. They're accessing this data with their ears. They want to be able to hear all of that amazing sciencey goodness tucked inside.
So, Kim, it seems to me you have more information than just the sound if you can listen to it in stereo, correct?
Correct, exactly. You can get a sense of that positional information. And also, what that helps do, I think, is make you sort of feel immersed in it, right? And I think that is sort of the gift of presenting it in this more musical, sound-based way. You have that sort of gift of time across, but also that immersive sort of opening to it.
Okay,
So,
let's do
yeah.
it in stereo, the center of the galaxy. Go for it. Okay, so the black hole in the center of the galaxy really fed that experience. But what about M87? That's one of the largest known galaxies in the universe, trillions of stars. It's got a Mondo black hole in its center, one of the biggest known. It's got jets, and you tell me you worked on that one as well.
Yes, we did actually create a sonification of M87 too, because that's another system that is supposedly also burping out into the surrounding gas. And from what I understand, the note might actually be pretty low, like 59 octaves below middle C.
Damn,
But that
damn.
sonification is a little bit simpler than the one that we just heard. It's more of a basic sound scrubbing across left to right, mostly the jet features that you're seeing in different kinds of light.
So you've isolated the jet to listen to
Exactly.
rather than all the
Yep.
downtown Times
Exactly.
Square behavior going on in our own galaxy.
Correct. Yes.
Got it, got it. So
Yep.
let's take a listen for that. Cool. So what octave did you put it in?
That one I don't actually know what the octave is. I could go look it up really quick.
But it would
Um,
be
that
accessible.
one was, yeah, that one was not, so we don't have the sound waves captured for M87 like we do for Perseus. So that one was just a scan of the jet data in three different kinds of light. So that one was a little bit different.
Got it. Got it. Understood. Understood. And so, and we have a third and final bit, but this is just a sampling of what is in your full portfolio. So we have the Chandra Deep Field. So what are we listening for here?
This is one of my favorites because if you've ever seen the image, it's not the most exciting, perhaps. It looks like you've taken a black canvas and just splattered some multicolored paint droplets on it, right? But the science of that data set is really important. It's the deepest X-ray image we've ever taken. Chandra looked at a patch of the sky for a really long time. I want to say it was about 40 days and 40 nights. Very poetic sounding. And captured like this landscape, if you will, of black holes. So thousands of black holes or very bright galaxies with supermassive black holes at their cores. And if you look at the image, it doesn't always communicate that as easily, right, to a non-expert. But when we sonified it, this is using stereo sound again, we scrolled from the bottom of the image to the top. The image itself, the X-ray sources, they're shown by energy level. So the lowest energy sources in X-ray are red, up to the highest energy X-ray in blue. And we can play with that. So the sounds are synthesized sounds, and you can hear the different energies of those X-rays as you scan.
You're telling me your acoustic map is better than the original data. That's what you're
It
saying.
actually
You're bragging
captures
here,
that a little bit. It captures more of that sciencey goodness than I think the image actually can, which was a really cool project.
And also, when you're orbiting Earth, you have to be careful what you mean when you say 40 days and 40 nights.
Yes, indeed. So Chandra, it goes about a third of the way to the moon. So it has a really lovely view of the universe, and the engineers had to work pretty hard to make sure Chandra would be able to capture all of that data across time. It wasn't a steady 40 days and 40 nights solid straight. Yeah.
All right, so let's give it a listen. So, Kim, this has been a delightful segment. When we come back, we're going to pick up our Cosmic Queries theme with questions given to us from our Patreon membership.
Sounds great.
And StarTalk returns. We're back, StarTalk Cosmic Queries edition. We're talking about sonifying the universe. Oh my gosh. And we've got one of the world's experts on that very topic, Kim Arcand. Again, Kim, welcome back to StarTalk. And I got with me my co-host, Matt Kirshen. And so, Matt, you brought questions with you.
I do, yeah. And I'll try and get through as many of these patron questions as I can.
Okay.
There's some really great ones. Some things you've already started to answer. So Malcolm Marfan from Trinidad and Tobago, you've already answered the first part of his question. But he also asks, how do you and your team decide which areas of the universe to study, and what factors go into making those decisions?
Oh, that's a great question. Yeah.
It's a big universe.
It is a big universe.
You're cherry picking it, right?
It's a big universe out there. So first, I guess what Chandra looks at is decided by a committee of scientists, right? So anybody can propose for time on Chandra, and those proposals are all put together and then like sorted through and decided on what Chandra will actually look like. And then time is, set to it, and Chandra's schedule is created, and all of that happens. So then when it comes to us to actually choose what we sonify, we're looking for objects that will sonify well, if that makes sense. So we're looking for things that will give us like a really nice landscape of something like the galactic center that we talked about earlier, a way to really get all of that really interesting science material translate into sound. Or we're looking at something like an exploded star that has a lot of detail in it, that as you're like scanning across it, like a radar scan, if you will, really lets you get a sample for what that object is like. So we're definitely cherry picking through the universe because this is more of a bespoke project. It's not an automated project that you can just scan everything with a push of a button. But what it does is it absolutely enables our friends and colleagues who are blind or low vision to be able to sample some of the most iconic and important data sets that we've got in our back pocket.
So it's interesting because we make a selection at any time for what we want to know about first and second and third. So what you're doing is no different from that. You're finding the parts of the universe that would be most interesting.
Yeah, exactly. Yeah, some of those really cool stories that need to be told through sound.
And earlier you were talking about 3D printing. You have a book that just came out?
Yes.
The title, Stars in Your Hand, a guide to 3D printing the cosmos.
Yeah.
That sounds a little scary. You don't want people printing black holes All right.
It's true. Though I actually do have a 3D print of a black hole with me today.
Oh,
But
you do?
indeed, it's a little guy right here.
Oh, okay. Cool.
But yeah,
Cool.
it's a thank you for asking about the book. It's fun. I like writing. I've been writing with my partner Megan Watsky for a while because I don't know. I love books, and I know other people do as well. And this book was just kind
That's
of
so
like
old-fashioned of you.
I
Oh my
know
gosh.
it is. I
Oh
will
my
take books
gosh.
over like TikTok any day. I'm just
Books don't even
old.
require batteries. I mean, what's wrong with you? You know?
I know. I'm very old fashioned. Vintage,
Hmm.
I think they call it now.
Okay.
Right? That's what they use. But yeah, I love books. And so for me, it was a great way to concatenate all of these cool 3D printable data sets of our cosmos into one place.
Okay.
It's just like a quick guide, if you will, to some of the cool sights to feel, I guess, versus the sights to see. So
Hmm.
things like exploding stars, galaxies, some constellations. I worked with a bunch of colleagues around the world and gathered a bunch of data sets into one place.
Okay. Excellent. And it's out now?
It is. It's out now, and it's meant to be a very gentle introduction. So even if you don't have a ton of experience with 3D printing or with the universe, it's a very gentle sort of workbook style feel to it to kind of give you a little intro.
Congratulations on it. Yeah.
Thanks. Thanks.
Yeah. So what else you got for us, Matt?
So I like this question a lot. This is from Tarina from San Francisco, who says, I work with visually impaired people, and we use lots of technology using sound waves to detect obstacles. Beeping gets louder when the device gets closer to the object, for example. Does the same thing happen in space, or do we need an atmosphere for this? Do radio waves bounce off objects? Is that one way to measure and or detect unseen objects?
Oh, that's an interesting one. Neil, do you want to take that one?
Well, I know. So it turns out there are not many telescopes in the world that have that dual capability. We had one. It was the Arecibo telescope, which collapsed out of misuse. But it was a huge radio telescope that can receive radio waves, but can also transmit. And so it's the transmitting that allows you to beam it at a thing that you can't otherwise detect and record the signal that comes back to you and make a map of it.
So this is like sonar, like a bat or a dolphin.
Precisely. It's sonar, but not with sound. It's like sonar, but with radio waves. I guess they call it radar.
Ah,
Radio detection
you
and
should
ranging.
trademark that idea.
Let's say that's a cool acronym right there. So for many asteroids that are just so small that a regular telescope can't really reveal what their surface looks like, then you have these radio wave topographic maps that you can create with them. So in a way, technically, you can measure how fast they're going, give them a speeding ticket, because that's what the cops do with their radar gun using microwaves. They beam microwaves at you and time the signal as it returns and invoke the speed of light, and they get exactly how fast you're moving. So there are things you can determine about these objects, but only in our solar system. Far away, it'll take years for the signal to get there. And by the time the signal comes back, you're not interested anymore. So, this idea of bouncing signals off of things, the best you can do is at the speed of light. And at distances in the universe, it's not a very practical solution for range, for getting the distances to things, or even for giving them speeding tickets.
I had no idea traffic cops were invoking the speed of light. They are
Yes,
much
they were.
smarter than I figured.
Yes, they are. Yes. Mm-hmm.
So Gavin Bamber, this is sort of like the reverse of what you're doing. So Gavin Bamber from North Vancouver says, please visit. And my question might be arcane for Arcand. I see what you did there, Gavin.
Oh,
but
Clever. Very clever.
But Neil, maybe Neil and Matt can provide assistance. I don't think so. I think the Neil part. But various wavelengths of light can be explained to a blind person in terms of varying levels of heat. But how can we translate the sound of the universe for deaf people to understand? So I guess this is sort of the reverse of you're converting signals into sound. How do we convert sounds into other signals for deaf people?
Yeah, that's it. Because Kim, you're focusing on sight impaired.
Yes.
And what about the hearing impaired?
Well, so for the most part, what we're doing is we're translating an image that already exists into sound. So for people who are hearing impaired, they do have access to that original image. But what we also do is we provide like a description of what the sonification is. So it gives a loose sense of what's included in that translation. But yes, things are going to be lost in translation. You can't really get the essence of the feeling of music through just words, but we do add that as a layer of accessibility to our products.
And I would add, if you have sight but not hearing, people with sight were not saying to themselves, gee, I wish I could hear the universe to understand it better. They would, they can see it, right? So
yes. So this whole project actually came about for two things in a way. So one, all of the sonification work that I've ever done has been inspired by my friend Wanda Díaz. She's an astronomer and a computer scientist who's been blind since she was a teenager, and she uses sonification to actually study stars. She had her whole PhD thesis kind of showed that scientists, humans, can become better listeners, right? And so that has always been kind of the inspiration point.
That's what every therapist says. We can become better
well,
listeners.
It's true. I think if everybody was a better listener, it would be a good thing.
A whole different world
right,
if that happened. Yeah.
Oh my gosh, yes, especially today. But also my friend and colleague, Christine Malek, she's been blind since birth. And so she's never seen the night sky. She's never seen any of these images. And for her, she's remarked to me that these sonifications, they're like a main meal where she gets her nutritional stuff from, versus somebody who's sighted who can access the images that the sound is like a dessert, right? It's delicious and it's another layer and you like it. But for her, the main meal is adding like the nutrition that she needs. And I love that way of thinking about it, because it does provide that, everybody has different access points into stuff, right?
So Kim, this is personal for you. I mean, you have close friends.
It's very personal for me,
gosh.
honestly. And so I'm like a super, super shy person, and at least I've always been super shy. And when I was a kid, I had a very hard time making friends. My very first friend in kindergarten was a little girl who was partially deaf. And she came up to me and she made me her friend. And she and her helper started teaching me sign language and all these things. And that's something that I have never, I know it sounds corny, I know it does, but that is something that I've never forgotten. I've never forgotten that someone helped me in those early days when I could barely move from behind my mother, right? And so I don't know, there's just this part of me that wants to look at the world like that. Do you know what I mean?
Yes.
Corny, but there we are.
No, it opens up a box that we don't even know we're in.
And also just how many potentially brilliant scientists were kept away from the work that they could be doing because it wasn't as accessible to them. And
right.
100%. Yeah. If there's anything that I hope comes out of this project, it's that. It's that I hope other people can sort of see themselves or picture themselves, envision themselves, hope for themselves to be scientists or just part of the science community,
Well, that's just part of the inclusion movement.
Yeah.
I mean, really.
Yeah.
I mean, if you want to think of it more holistically than that. Yeah. Matt, give me some more.
All right. So Connor Holm from Squim in Washington. There's a pronunciation guide. I appreciate that, Connor.
Squim? That's a place in Washington? That's
Squim. It spells Sequim, but then there is a pronunciation in brackets afterwards.
Squim, thanks. I'm glad, because I never heard of the town.
Yep.
All right, cool.
Never knew, but Connor says, really love the show. What is the most active electromagnetic wavelength in the universe? Also, are all wavelengths found everywhere in the universe?
That's a great question. I mean, Neil, I'm sure you have better answers for these things because I love the way your mind works. But, the more energetic you get, obviously, it's going to be very, very active. So that's how I'm thinking of active. So I would say things like gamma rays and X-rays are going to be the most energetic regions of the universe and hence the most active, sort of. But there are less X-ray photons in the universe overall. So maybe that's not the perfect sort of way to think about things.
I like that.
I don't know.
I like that distinction you're making. Yes, so there are places that have very high energy output, all right, in X-rays and gamma rays. Those are the highest energy variants of photons of light. But if you're in another place where it's giving out mostly infrared, but boatloads of infrared,
right,
then the total energy budget might be higher there than where your single high energy photons might be found. So
which one?
That's an excellent distinction to make. But the whole electromagnetic spectrum, as we've discussed in StarTalk explainers before, it's the full range. You go from radio waves, microwaves, infrared, visible light, red, orange, yellow, green, blue, violet, ultraviolet, X-ray, X-rays, and gamma rays. And that sequence is a sequence from low energy to high energy. And not all parts of the universe give equal amounts of those bands. And in fact, we didn't know that the universe was talking to us in bands outside of visible light until we discovered invisible light. And they'd say, well, wait a minute. Our eyes aren't think about it. If you were religious, why would God give you eyes that can't see everything you want to see, right? The people had to figure this out. What does it mean that there's stuff going on that our biophysiology has no access to? And so it took the methods and tools of science to discover ways to discover and detect and figure out ways to detect infrared, ultraviolet, X-rays, gamma rays, and we've exploited them all in our modern civilization, which is a great triumph of 20th century physics, I would say. But yeah, so X-rays enabled us to see black holes, to discover the vicinity of black holes. Gamma rays, we found bursts of gamma rays in the universe. We didn't know they were there. Infrared, we find deep gas clouds that are birthing stars. Each of these bands is a different window to this universe in which we're immersed. And so, yeah, and now, Kim, with what you're doing, you're opening up windows of access to those windows that are otherwise invisible.
Right.
So,
yeah, that segues back to what our discussion is so well.
Completely.
Right? Because what are we doing when we're studying X-ray astronomy? We're transcending human vision, right?
Yes, yes.
And so then that we can take the data and translate it into some other way of knowing, some other way of making meaning through sound or perhaps taste or scent, though I still object. But
I'm waiting for that. You call me, okay?
I've read comic strips. I know smell has waves. It's
I'm kind of picturing those 1980s, 1990s scratch and sniff stickers or something.
Smell-o-vision.
Is that what's in my future? Is that what you're saying? I don't know. I don't think so.
It's next. Matt, let's slip in one more question before we take a final break.
This is sort of connected. And by the way, I'm filling in for Chuck, and this patron says, Chuck, you're the only person to pronounce my last name correctly on first attempt, so let's give this a go.
We've got to tell Chuck that.
Let's give this a go. I'm going to go with Colby Laprezi from South Carolina. Sorry if it's Laprezi or anything else. But it says, I'm wondering why a pulsar is best seen in X-ray and radio wave. Seems contrary. Thanks. Love the show.
Okay, cool. In fact, we're going to take a break, and we're going to come back to that very question. X-rays and radio waves, they do seem contradictory. We're here with the world's expert on sonifying the universe when we come back. We're back. StarTalk. Cosmic Queries. Matt, what do we call this edition? Sonifying the universe? Not personifying it, but sonifying.
Sonifying. Let's get this thing generally sonifying, not just for you, it's for everyone.
Yeah, that's right. Not personifying. Sonifying the universe is for everyone. Kim Arcand, delighted to have you back as our guest on this fascinating subject that we're learning that it goes deep with you, not only personally in your life experience, but as a child, but with friendships that you've carried throughout your life.
Absolutely.
We left off. Matt, read that question one more time.
Yeah, why is a pulsar best seen in X-ray and radio wave? Seems contrary.
Well, I can add that, pulsars are really fascinating objects because they're like the leftover cores of stars that have passed on, exploded, if you will, exploded their guts out all over the universe. And so all of that material that's packed in there, it's superheated, it's super exciting, great for X-rays. But it is always interesting to me how well X-ray information and radio information do complement each other, not just for things like pulsars, but things like galaxies, things like supernova remnants. And Neil, I would love for you to talk to us about that.
No, this is great. It's a brilliant answer. When you have a place like a pulsar, which is extremely hot, anytime you have very high temperatures in the universe, things happen that give you high energy photons. So X-rays and occasionally gamma rays in the most extreme case. But also, a pulsar has a magnetic field. And a magnetic field, when it interacts with some of the particles in its vicinity, will generate radio waves. And so for example, Jupiter has a very strong magnetic field and a strong radio waves that it emits. So, in fact, Kim, have you thought of acoustically representing the planets, those that have sort of radio wave emission? Or
yes.
you just badass things out in the far reaches of the universe?
Like, I do like the higher energy work. I won't lie. But so there is actually some really cool data sonification work on some of the planets that Matt and Andrew have done at System Sounds, and we are actually working on some related stuff right now. Yeah.
Okay. Yeah. Very good. Very good. So no part of the universe is out of your purview.
Nope.
That's very good. So Pulsars gives you both ends of the spectrum there because it's doing more than one thing. And we have magnetic fields. You tend to have radio wave emissions, and high temperatures. You'll get higher energy light. So that's all that's happening there. It's not magic or anything.
It's a great question.
Yeah.
And they do complement them so well. They do.
Indeed. And it makes for more interesting sonification projects.
Yes, exactly. Yeah. And we have actually sonified the Crab Nebula pulsar. So that might be one that your listener might want to take a listen to.
Mm-hmm. That was the very first pulsar.
Yep.
The one in the center of the Crab Nebula. First known
gorgeous
pulsar.
Gorgeous.
Yeah.
One.
In fact, there was giving us pulses. And what else can you think if nothing in the universe ever gave you such regular signals, such reliable, repeated signals? And we were sure it was little green men.
I know. It did seem suspicious. But fortunately not. Fortunately not.
Yeah. Nature can do that, it turns out. But had it been giving us digits of pi, then that's another thing.
Right, yeah. There's more reason to be worried.
All right, Matt, keep going.
All right, I'm going to combine a couple because we've got a lot to fit in. But
I still want to hear who
oh, absolutely. Yes. Mm-hmm. Yeah. So I'm going to combine a couple because we've got a lot to fit in. So Daniel Johansson wants to know what other wavelengths or types of telescopes could bring us new views on the universe in the future. And Biren Amin from Florida says, if you had to design any instrument to begin answering more complex questions, what would be the ideal properties it would have?
Ooh. Well, let me lead off, and then Kim, you pick up the baton here. So a new telescope that came online within the last 6 years is LIGO, the Laser Interferometer Gravitational Wave Observatory. It's discovering gravitational waves from colliding black holes that have been moving through the universe for billions of years. And that's so, Kim, that sounds like a natural to turn that into sound.
Yes, and actually I'm pretty sure that someone has done that work, and I forget who it was, but I'm pretty sure someone has done that already.
This is me jumping. I'll take this one, guys.
Okay, great.
Okay.
But I seem to remember on this show when we were here with Jan 11, who is all about black holes and radio waves, and gravitational waves rather.
Yes.
She played an audio representation of two black holes colliding, which actually one of our Patreon patrons asks about. This is Troy from the DMV area asked about, said it sounded like a drop of water. And does the universe sound like water because of all the waves floating around?
Oh, I remember, because it was as the black holes spiraled closer and closer and more tightly, the way they sonified it, it was like rip, rip, or it was like a drop of water.
I pay attention. I listen in class.
Matt, in fact, we have that sound right now. Check it out. So, Kim, how'd they do?
I think they did pretty well, though I'm, of course, partial to our own technique. I think it's a really interesting way to represent data. And anytime you can open up access like that, it's an absolutely worthy endeavor. So, yeah, A+.
Okay, excellent. And another kind of telescope we don't quite have yet. We have detectors, but not really telescopes. You can detect something but not know anything about the object. You just know that you detected something. So that's the difference between a telescope and just a bare-ass detector sitting out there. Neutrinos are not light. They're not gravitational waves, but it's another thing in the universe moving through the universe that comes from some places and not others. We have neutrino detectors, but not really neutrino telescopes. So that'd be another frontier that we can put on the docket. The day we have a telescope, Kim, I want to see you lined up right at the door.
For sure. And if I could just add, it's kind of a cheat, but I also would love to have access to a next generation Chandra. Chandra is almost 25 years old. It celebrates 25 years next year. And yeah, we could definitely use for like a bigger, more powerful version than next generation.
Just tell
Chandra.
Congress and get the $10 billion. That's all.
Ah, right. James Webb, but in X-rays, please. Could someone deliver that? That would be great.
Oh, yes, that's the helpful reference point. Yes. Yeah. James Webb, but in X-rays.
Right.
You got it.
Yeah.
Okay. I'll write that check.
Small
yeah, well, you've just answered Nick R. from Texas's question right there, so I'm going to jump on to Kenneth von Smelsmore of the Atlanta von Smelsmores, who says, Sight and
we all know the Atlanta von Smelsmores, of course.
Very official.
Sight and hearing are senses we developed here on Earth using the physics of our environment. We know other animals can sense other phenomena like magnetic fields. How might an extraplanetary being sense and communicate? Would a four-dimensional space whale sing via gamma rays? Could they feel via gravitational waves?
Wow.
I love that.
Wow.
Kim Arcand, how much effort do you put in to thinking about alien sensory systems?
None,
or are you boxed into being human?
Yeah, so I was all proud of ourselves for like transcending human vision, but
you just got called out.
Yeah,
you just got busted.
I feel so boring and vanilla right now after that question. That's pretty intense.
Yeah, I can address that. I can't answer it, but I can toss some words in that direction. And I can say that in science, we've known maybe for 300 years that our five senses are not telling us everything that's out there. And when we first discovered infrared, we said, well, could there be even more than infrared? And then that's how we start filling out our ability to know the world in which we're immersed. I can say without hesitation that the methods and tools of science have developed at least a dozen senses. Right, well, there could be magnetic fields, gravitational vectoring, polarization of light. These are things you cannot see. You cannot experience. We don't have the means of experiencing it, but our methods and tools of science can. So I say to myself, if an alien has extra senses, why wouldn't they just be drawn from what we already know we can determine by science? Just because our physiology doesn't get it, our science can. Which means when someone walks out, and Kim, I don't know if you feel this, someone says, I have a sixth sense. And I say, I'm not impressed. I have 12 senses. Come into my lab. You'll see every sense that we've got. So, yeah, it would be fun to just think about, just broaden what it is you've done. Yes, a lot to be proud of, but maybe that's just the beginning.
That's it. I love when people think big, right? And I love when you're thinking outside of the box because, even with this project, there were people that were sort of like doubting, is adding sound really worth it? Or with 3D printing, is like that really necessary? And each time we've tried one of these projects that just goes a little bit, into a strangely new place, we keep getting rewarded for it. So yeah, thinking creatively, thinking big, it's really worth it. It really is.
Love it. All right, Matt, give me some more. 3 minutes. What can we do in 3 minutes?
Uh-oh.
We can speed through a few.
We'll see how good Kim is with sound bites. This is
I'm very bad with short answers.
This is your next
very
test.
Bad.
Okay. Go ahead.
Anthropocosmic Dylan from San Diego says, how is the information carried by X-rays and other electromagnetism different from information carried by mechanical waves like sound?
Oh, that's a great question. That's too physicsy for me.
Light is just photons.
Yeah.
Just photons. And there's the good photon joke. You ready? Photon checks into a hotel. And the bellhop says, do you have any luggage? And the photon says, no, I'm traveling light.
That's cute. That is really cute.
That's even safe for elementary school. So, yeah, so it is a self-propagating wave, which was an amazing discovery when it was made in the late 1800s. And sound is energy pulsing through a medium. And yeah, this is the issue about sound getting to us through the vacuum of space. which it can't.
Well, Joey Santos also asks, is there any medium that sound can potentially travel through in space, like a dust cloud or trapped particles, which I think you answered a bit in the area around black holes, but...
Yes, absolutely.
Yeah, any of that.
Absolutely.
Exactly. And
dusty particles around stars, any
this
kind
is
of
her total
disk. Yes, yep.
That's your palette.
Yes, yep.
Yes,
okay.
I love it.
Sam Pennington from Texas says, I've been listening to audio files that say this is what Jupiter sounds like. Is that really what Jupiter sounds like, or is that a compression of the spectrum into audio form?
So I don't know what he's listening to or what that person is listening to, but I know there is a scientist, Bill Kurth, I think his name is, that does a lot of interesting stuff with planetary data. He's using things like radio emissions of auroras from Saturn, perhaps from Jupiter too, plasma oscillation.
Well, you just blew by that. So Saturn has aurora borealis just the way we do.
Yeah.
You just blew through that.
Oh, sorry. Well, I'm just trying to get through it fast. I thought I was so fast.
That is true. I did rush you, and you're fulfilling the mandate, and I am stopping that. Okay, yeah. Earth is not the only planet in town with the northern lights and the southern lights.
That's good to know, because it's expensive to get to Iceland right now. So
That's it. If you have a magnetic field, as we do, and an atmosphere, and the sun has its charged particles, it'll render your atmosphere aglow. And that itself generates radio waves. So that's where you just blew right past that, Kim.
But there are great sonifications of those. So it's possible that that's what they've listened to. That's a guess, at least. It's possible that that's what they've listened to. That's
Dr.
a guess,
Edwin Florence from West Lynn, Oregon says, since the James Webb has provided very fascinating data from the infrared part of the spectrum, what data do you hypothesize the Chandra project will provide from the shortest wavelengths of the spectrum?
So I think, Chandra has been providing fantastic data of things like exploding stars, things like colliding galaxies, merging black holes, pulsars, you name it. I mean, you find a lot of X-ray data, more than I ever would have expected. And what's actually pretty cool about it is Chandra data and Webb data complement each other very, very well. So we're actually in the process of working on a sonification right now that combines James Webb data and Chandra data of the Stephan's quintet. And actually, I think that should be out in like another week or so.
Stephan's quintet is one of the first images released by the James Webb Telescope.
Exactly.
The 5-galaxy interaction.
And there's like these beautiful pockets where the X-ray data just kind of fills in like a bridge in between some of those interacting galaxies. And it's a really lovely way to experience the data. So yes, more on that soon.
Again, you say this casually, but I want to emphasize that when you have two completely different telescopes observing the same object, they're going to reveal different things to you, but maybe those two different things connect in some way. Physically, in terms of what a phenomenon going on inside. And so this is extraordinary vision to bring to bear on these objects when you have completely different telescopes looking in the same direction, especially at the same time.
Yep,
so
it's powerful.
Very cool, yeah. All right, Matt, she's doing pretty good, isn't she?
I mean, I'm trying. They're hard.
She's got the quick answers. Go.
I like to answer long, so this is hard.
And I've been slowing you down. I've been messing with your mojo here. Okay, we got
so this is
one more question.
Okay.
So last question, we'll squeeze this in. Bill Bailey from Ohio says, speaking of hearing the universe, will we know the difference between the sounds or gravitational waves created by the Big Bang and those created by ultra/supermassive black holes?
Oh.
So, like, more than just the cosmic wave background kind of thing? Is that what?
Well, no. We're talking about the Big Bang itself.
So, like,
would be responsible for even before the cosmic background. Yeah, it seems to me that'd be if we do the calculation right, it should look different. It's a different phenomenon. Right. If you want to blow the universe into existence, it seems to me that would have a different signature from two colliding black holes.
Right. And
would you agree with that, Tim?
That would be great to hear. So yeah, let's do it. Let's capture that.
And what would that be? That would be like the ending bombastic finale to a classical symphony?
Yes, exactly. And yes, actually, thanks for cueing that, because I can say one of the really interesting extensions of this project has been whenever we talk about sonifications, there are musicians in the audience and they want to play the sounds. They want to play the data. And so we're actually working on that. I'm working with a young composer who's very talented, and she's translating the sonifications into stuff that's playable by humans with their instruments.
So
such
I
as
think
flutes, violins, all of that.
So I think for the Big Bang, every
So what do we
instrument
need?
has to be playing
Yeah.
simultaneously at its loudest.
Absolutely.
And that would be the Big Bang.
Absolutely. Lots of percussion.
Lots of percussion.
I don't know. I don't know about the slide whistle.
That is not the time to hold back.
All right, fine. Every instrument ever known to humans, bring it in. How's
At
that?
full volume, there's the Big Bang for you. We got it. We don't even have to.
That might be pretty cool.
Yeah, it would be totally cool.
Yeah.
All right. Well, Kimberly, it's been a delight to have you back. This is your second appearance on StarTalk.
Thanks.
It's great to check in with you, and you have this new book out, the 3D printing of the universe, and the full title is
Stars in Your Hand, which I think
Stars
is kind
in
of
Your
fun.
Hands.
Yep.
Very, very poetic.
Thank you.
We love it. Matt, thanks for being with us here. And Kim, where do we find you on social media? What's your footprint?
I'm on Twitter and Instagram, I think at Kimberly Cowell for both. And then you can hit me on my website, Kimberly Cowell, Kowal. It's from when I had my maiden name a long time ago.
Oh, it's left over.
Yeah,
okay,
it's left over from ages ago.
Left over.
And then my website is kimarcand.com.
Kimarcand.com. All right, we can totally find you that way. All right. Thanks for being on StarTalk. Matt,
Thanks.
always good to have you here, man.
Always good to be here.
All right, this has been StarTalk, Cosmic Queries Edition. What the universe sounds like to us all, but especially to Kim Arcand. Right. Until next time, Neil deGrasse Tyson here. Keep looking up.